record this too. Okay, so this is just, I hope this is right. I'd be embarrassed if it's not, but I took the, so this is the fourfold rotation around, I just took Z as the axis that I was going to rotate around. So this is fourfold rotation around Z, and then I invert it. So this is your typical roto inversion with the rotation down Z, and then this is the matrix that I get out in the end: 0, 1, 0, minus 1, 0, 0, and 0, 0, minus 1. So if you start off with coordinates x, y, z, and then if you apply this matrix, so if you multiply this matrix by x, y, z, then you will end up with y minus x minus z. And then if you repeat that, then you end up with this another set of coordinates: minus x minus y z, and also minus y x z. So I did the same, but I took the fourfold rotation around Z, but now I also, instead of inverting this structure with the inversion center, I mirrored it perpendicular to Z with this matrix to give you a different matrix. You see, it's a bit different. But if you start off with x, y, z, and or if you multiply this 3 by 3 matrix to x, y, z, you end up with minus y x minus z. Now, even though this matrix is different, I think we go in opposite order. So actually this minus y x z, it's actually this coordinate here. And if you apply this matrix again, you end up with these 4 equivalent points. And as far as I can tell, these 4 coordinates are the same as these 4 coordinates. So even though the matrices are different, they just kind of give you the same coordinates, but in different order. So yes, I would say that doing a fourfold rotation and inverting it would be the same as doing a fourfold rotation and mirroring it. But for these other examples with the 3 bar and the 6 bar, the amount you rotate would be different. So, but you could, again, using matrices and showing the symmetry equivalent points, show if those would be the same or not. So this is a really good exercise, I thought so. So I hope with the course that you will become comfortable testing these things yourself too. Okay, but let's go back to the lecture. So I'm going to stop sharing that screen, and then I'm going to share the screen in presentation mode. So one moment, please. Sorry, I'm in the wrong place of my slides now. Okay, so let's go back and share the presentation mode. All right, so so we've covered point symmetry now, but we're also going to talk about other forms of symmetry that aren't examples of point symmetry. So these are symmetry operations that involve some translational component. So yeah, if we have 1-dimensional, 2-dimensional, or 3-dimensional structures or translational symmetry, then we can start talking about plane groups and space groups as well. Okay, so in 2-dimensional symmetry, we might have, a unit cell, a 2-dimensional unit cell like this. We've already talked about 2- and 3-dimensional unit cells. But when we talk about translational symmetry now, with the previous examples of symmetry like rotation and inversion, we did some matrix multiplication. But now what we're going to be doing is matrix addition to talk about and describe translational symmetry. So say you have, again, fractional coordinates x, y, z. If you want to translate it, then you can add a 3-by-1 matrix to it. So you can add your translational components A, B, and C. So say you just want to go 1 unit cell, down in the x direction. So then the equivalent point would just be, A would be 1, B would be 0, and C would be 0. So then x plus 1. YZ would give you the equivalent position 1 unit cell down along the X or A directions. Okay, so also centering we can describe using a 3x1 matrix. So like with A centering, for example, when we have base centering, but maybe you don't have to always have that base centered on the C face, that AB plane. You can have A centering, say, for example, so that would be in the BC plane. So that would be like this face here, up in the front of this face. That would be the A-centered face. That we can describe a similar. So let's focus on this C-centered, base-centered, this one here, because that's what we see in this image here. So if you start off with the origin, let's say it's this point here. The C-centered equivalent position would be half of a unit cell length along X. So that would be, I guess, A is here. So this would be halfway along X, but also halfway along Y. So then we go half a unit cell in that way. So half along X, half along Y. That's our C-centered equivalent position. I-centered, we go halfway along A, B, and C. So we have, a half, a half, a half for the three values of the 3x1 matrix. With F centering, it's a little bit more complicated because all of the faces have centering. So, so you can imagine this as a combination of A centering, B centering, and C centering. So again, A centering, B centering, and C centering to get all of those symmetry equivalent positions. So glide planes now. So glide planes are a combination of mirrors with translation. So right now we just see butterflies related by translational symmetry. But let's say we have a glide plane. So mirror planes are usually bold, kind of solid lines. Glide planes are often represented with dashed lines. So say we have a mirror, a glide plane in this case. So the glide plane is perpendicular to the y-axis. It runs along the x-axis, but it's perpendicular to the y-axis. For mirror planes and glide planes, we very often use the direction that is perpendicular to describe the position or the orientation of the plane. So say we first mirror it, but then we need to translate it. So what we've done is we've mirrored it along the glide plane, but then translated it halfway of the full unit cell length along the x-axis. So mirror plus half, a translation of half a unit cell length along the x direction. So again, we can use matrices to describe this. So we have a combination now. So here, this 3x3 matrix describes a mirror plane perpendicular to the y-axis. Plus we have that translation of half a unit cell along the x direction, unit cell parameter A. So yeah, x plus a half minus yz, this is going to correspond to your mirror plane. Your glide plane. But yeah, so in 3 dimensions, glide planes can become just a tiny bit more tricky because we can have glide planes, different types of glide planes. The translational component can be in different directions. So we're going to cover these now. So let's say, let's start off with our A glide. This is a type of glide plane. So this is what I've drawn here. This is an A glide, which is perpendicular to the y-axis. So like mirror planes, with glide planes, we always, have to describe which direction that plane is perpendicular to. So you see this plane that I've drawn here, it's in the XZ plane, and it's perpendicular to the y-axis in this particular case. So why is it called an A glide? So the A indicates which direction the translation occurs along. So in this case, the translation is along the x-axis, half a unit cell along x. So that's why we call it an A glide. Now, if we were to have a C glide, so this C glide plane now, it's still perpendicular to the y-axis. That hasn't changed. But the direction we translate along now has changed. So now we're translating half a unit cell along Z, which is why we call it a C glide. We can also have an N glide. So an N glide now, again, this is an N glide still perpendicular to the y-axis, but now the translation is halfway along X and also halfway along Z. So the translation is kind of a diagonal now, both along X and Z in this case. You cannot have a B glide perpendicular to the y-axis. So the direction you translate will not be this perpendicular to the plane that you're reflecting along. So in the if you have a glide plane perpendicular to the y-axis, it can be an A glide, or a C glide, or an N glide, but not a B glide. You wouldn't see that. You can have a B glide if it were perpendicular to another direction. For example, like if the glide plane were perpendicular to X or Z, then you can have a B glide. There's also something called a D glide, a diamond glide. This one's a little bit trickier. So say, again, with every glide plane, you have a direction that the plane is perpendicular to. So this is a D glide perpendicular to the y-axis again. So with a diamond glide, this happens only when you have a centered lattice, like an F-centered or an I-centered lattice. So say first, we start off with this butterfly in the origin and we mirror it. Now the direction we translated, the vector we translated along, it's going to depend on the centering. So in this structure, say if we start from the origin, this is a body-centered, an I-centered lattice, which I've drawn here. So there's a vector going from the origin to the centering point. So this is a vector that goes half along X, half along Y, and half along Z. Half, half, half. So with a diamond glide, you go half the distance. You translate half the distance of that vector. So from here, after we've mirrored it, you translate it. So again, the translation is half the distance of going from the origin to that centering point. So this is what a D glide is. All right, moving on to screw axes. So these combine rotation and translation. So a 2-1 screw axis, for example, it combines a twofold rotation plus a translation of half a unit cell. And the translation is always going to be in the same direction as the rotation axis. So this is oval. Let's say this is just a normal twofold rotation axis. So if I have a position here, if you rotate along this rotation axis, then your equivalent point is here. And this is just one unit cell up along that same axis. Now, if you were to have a 2-1 screw axis, this is the symbol for it. It looks more like a propeller. So you rotate 180 degrees, a twofold rotation, and then you translate half a unit cell up along the same direction as that rotation axis. So this is going to become your symmetry equivalent position. And if you repeat this again, rotate it 180 degrees and translate it half a unit cell up, then you end up on the equivalent position on the next unit cell. So we can also have 3-1 and 3-2 screw axes. So again, on the left-hand side, this is just your standard rotation axis, a threefold rotation axis. So these 3 points are related to one another by a threefold rotation. But in a 3-1 screw axis now, you rotate 120 degrees, but then you rotate, you translate 1/3 of a unit cell up. You can repeat this again, rotate it 120 degrees and then translate it 1/3 of the unit cell length along the axis, and you end up at this point. And then you repeat this one more time, rotate 120 degrees, translate 1/3 of a unit cell up to end up with the equivalent point in the next unit cell. So this 3-1 screw axis, these 3 screw axes you can imagine as being helical. And the difference between 3-1 and 3-2 is that you just rotate in the opposite direction. So in this previous example, we were rotating it, say this way and translating up. In this case with 3-2, we're going to rotate it the opposite direction, this way, and then translate it up the same direction. And again, if you repeat this 3 times, you end up with the equivalent points, 1 unit cell up. So you can imagine like the 3-1 screw axis and the 3-2 screw axis. These are related by mirror symmetry. So say if you were to have, a chiral structure that is enantiopure, it might be just 3-1. But if you have the opposite handedness, the enantiomer, it might be just 3-2. We can also have, screw axes that are related to fourfold rotational symmetry. So we can have 4-1, 4-2, and 4-3 screw axes. Let's start off with 4-1. So with 4-1, probably not so surprisingly, you rotate it 90 degrees and then you translate it 1/4 of a unit cell up. I like to imagine it, so to get the amount that you translate it, it's just kind of, I like to imagine it as like being 1 divided by 4. So you can get it from the numbers here. That only really works like when you have the number in subscript as 1. So you can repeat this 4 times and then you end up at the next unit cell here. With 4-3, again, it's the opposite direction you rotate around. So instead of rotating it, say positive 90 degrees, you can rotate it negative 90 degrees, let's say. So this is again a helix, but going the opposite direction. So I think with 4-1, you have a right-handed helix. With 4-3, you have a left-handed helix. 4-2, what is happening here? So with 4-2, so this 2 in subscript, I like to imagine it as you have twofold rotational symmetry now. So you see along this screw axis, there's an equivalent point related by a twofold rotational symmetry, this position here. But to go from these 2 points to the next 2 points, we still have to rotate it 90 degrees. That's why it's fourfold. We have that 4 as an integer. So we have a fourfold rotation, and then now we translate it half a unit cell. So again, 2 divided by 4 is what I like to imagine it. And if you repeat this process 1 more time, rotate this 90 degrees and translate it half a unit cell, then you end up at the next unit cell. And with 6-fold screw axes, it gets a little bit more complicated. We have a few more of these. So again, I think the simplest is the 6-1 screw axis here. You rotate it 60 degrees and then you translate it 1/6 of a unit cell up along the screw axis. And you can repeat this 6 times to get to the next unit cell. And 6-5 is the opposite handedness of 6-1. Okay, let's talk about 6-2 now. So again, the 2 indicates you have a twofold rotational symmetry as well. So there is twofold symmetry, but now it's still a 6-fold. So we rotate it 60 degrees, and now we translate it 1/3 of the unit cell up. So that's like 2 divided by 6 gives you 1/3. So that tells you how much you can translate. So this only works kind of when you, where the number in subscript is, up to a half of the larger number here. So again, you can repeat this 3 times to end up at the next unit cell. And 6-4 is the kind of the opposite handedness, the mirror image of 6-2. So these are all helices again. So helices can be right-handed or left-handed. So what's happening with 6-3? So the subscript in 3 tells me that there is 3-fold rotational symmetry. But to go from this plane, again, we rotate it 60 degrees, and now we translate it half a unit cell. So 3 divided by 6 gives you a half. That's the amount we translate by. So if you repeat this twice, you end up on the next unit cell. Okay, so like I said, with the example of zeolite, I already said, yeah, there were more than 500 atoms, actually, to be more precise. There's 576 atoms. That means there are 1,728 fractional coordinates that you need to figure out. You know, for every atom, there's X, Y, and Z. So that means there's 1,728 parameters that you need to get to describe all of the atoms in one unit cell. That's quite a few parameters you need to know. But again, with just the asymmetric unit, just the position of these 5 atoms, 1 aluminum, 1 silicon, and 3 oxygens, that means we only have 5 unique atoms in the crystal structure, which means we only need to figure out 15 positional parameters, 15 values for X, Y, and Z in the whole structure to actually be able to describe essentially every atom in the crystal. Now, why are parameters important? So for every atom, we have our fractional coordinates X, Y, Z. So those are 3 parameters that describe the position of the atom. You might have another parameter to describe the atomic or the displacement parameters. This kind of describes how the electron density is spread around that atom. So if you use isotropic displacement parameters, if you describe that electron density around an atom as a perfect sphere, there's only one parameter, one isotropic displacement parameter that describes, how large that electron density is, or how small it is. If you use ellipsoids to describe your ADPs, your atomic displacement parameters, then you need 6 anisotropic displacement parameters to describe that ellipsoid. So it's a shape that's more complicated than a sphere. Typically, we want to use anisotropic displacement parameters to describe the electron density around your atoms. So that means if you use anisotropic displacement parameters, then you have 3 fractional coordinates and also 6 anisotropic displacement parameters. So that's 9 parameters per atom. But you might also have other parameters like the overall scale factor, which I think Lasse will talk about. You might have other scale factors, which we'll talk about when we start to introduce the program, ShellX. If you have a chiral structure, and if you're interested in the absolute structure, then the Flack parameter is also yet another parameter that's added. So there's quite a few parameters that you have when describing a crystal structure. And all together, you want to have the number of parameters to be roughly, it's going to be roughly about 10 times the number of unique atoms that you have in a crystal structure. That's just kind of like a rough rule of thumb. But the more parameters you have, the more complicated it is describing that structure. And also the amount of data you have is limited. So by data, what I mean is the number of reflections you've collected in your diffraction experiment. So this ratio between your amount of data and the amount of parameters you have, it's quite important. So you want the data to parameter to ratio, the ratio to be quite high. That means you have a lot more data than parameters, let's say, is the ideal case. So for non-centrosymmetric structures, you want this data to parameter ratio to be 8 or larger. For centrosymmetric structures, you want it to be 10 or larger. And if that doesn't turn out to be the case, the refinement can become unstable. So if it is, if you have less data than parameters, then your refinement is not going to converge, say, and it could explode, and you end up with a very unreasonable structure model in the end. So it's important to have much more data compared to parameters in your refinement. Okay, so we're going to move on to talking about combinations of symmetry now. So we've talked about the individual symmetry elements and symmetry operations. But of course, in crystal structures, you might not just have one symmetry operation. You might have several of them. And there's only certain combinations that you can have, which we'll talk about when we describe plane groups and space groups. So it becomes important to be able to identify these different symmetry operations in our crystal structures. So perhaps if you're new to crystallography, these symbols might look foreign to you, but I hope by the end of the course, you'll be able to recognize these symbols. So these symbols represent the symmetry operations that we have now gone through. So for example, a twofold rotation axis is symbolized by this kind of oval shaped symbol. If the axis goes into the page, so this first row here shows rotation and roto-inversion that are going into the page. Now the next row of symbols here, these kind of arrows, these correspond to still rotation and roto-inversion axes, but now this corresponds to axes that are in the that are kind of parallel to the plane that we're looking at, so running up or down, let's say. So yeah, threefold rotation is a triangle, fourfolded square, sixfolded hexagon. And if you see like a dot or kind of these empty white spaces, they correspond to the fourfold and sixfold roto-inversions. With screw axes, you have these kind of struts coming out. So they look similar to the rotation symbols, but now we have these kind of propellers or struts poking out of them. And depending on which direction they go and how many you have, they might, represent if it's, a 6-1, a 6-2, or 6-4 and whatnot. So again, 6-2 and 6-4, they're related to one another. So the symbols also look the same, but they're related by mirror symmetry, as you can see. An empty circle like this corresponds to an inversion center. Like I said, mirror planes are represented by solid lines. Glide planes are represented by dashed lines. Now, depending on what sort of dashed line you have, will tell you, whether if it's this simple dashed line, then it's an A, B, or C glide. If it's an N glide, it'll be dashed lines with dots as well. If you have a diamond glide, then you might have this arrow there. And E-glides. So E-glides, I have not mentioned them yet. And actually, they're a newer symbol that were introduced. So if you look at kind of older textbooks, you might not see an E-glide, but this has come up more recently. An E-glide, it's actually it's a combination of A and B, or A and C, or B and C. So if you have both, so say you have a glide plane that's perpendicular to, say Z in that case. So then you can have an A glide or a B glide. But if you have both an A glide and a B glide, then we call that an E glide perpendicular to Z. So E is just a combination of two of these three, A, B, and C. So in 2 dimensions, you can only have 17 different combinations of symmetry elements. So we call these the 17 plane groups. We'll be going through those today. And then next time we have a lecture, we'll be talking about the 230 combinations of symmetry that you can have in a 3-dimensional crystal structure. So these are the 230 space groups, which will be the topic of the next lecture. All right, so let's look into these 17 plane groups then. So in 2 dimensions, we can have translational symmetry. Again, this will be represented whether if you have a primitive or a centered lattice. We can have rotational symmetry, 2-fold, 3-fold, 4-fold, or 6-fold. We can have reflection and glide planes, and that's it. Everything else would be kind of the non-standard form. So like we said, with the crop circles. A twofold rotation in 2 dimensions is actually the same as an inversion. But the standard way would be to describe that as a twofold rotation rather than an inversion. It's just the standardized way of doing things. So with translation, again, we talked about this last time, we can have primitive or centered lattices. With rotations, we can have twofold, threefold, fourfold, or sixfold. We don't have fivefold rotational symmetry if you have a periodic structure in 2 dimensions, because you can't describe, or you can't fill 2-dimensional space only with regular pentagons, let's say. You'll end up with gaps. So you can't really have a pentagonal unit cell without leaving some gaps in the structure. Of course, with quasi-crystals, you can have kind of local fivefold symmetry, but you don't have one unit cell in that case to describe the crystal structure. And we're not going to be talking about quasi-crystals in this course. So we won't be concerned about fivefold rotational symmetry. Okay, so let's do some examples together. So I have a picture on the right-hand side. There's some periodicity in 2 dimensions. So there is a 2-dimensional unit cell, and there's some symmetry. So I'll go through this example together with you, and then I have some examples later on if there's time that you can do on your own, or as a group. That would be even better if there's some discussion. But let's go through this example together. So to identify symmetry, usually I like to start off by looking at the unit cells. So this is a unit cell that I've picked. I just took the center of the red dots and connected them up. So we have this unit cell, but there is some symmetry. There are mirror planes. Now there are mirror planes that cut through the stars. So the left-hand side of this star ends up being the same as the right-hand side. But there's also mirror planes between the stars. So that relates, say, this star here on the bottom left. If you mirror it along this mirror plane, then you end up with this star here. So you have mirror planes both going through the stars, but also between the stars. Now, in this next example, glide planes are a little bit trickier to see. So again, I've picked a unit cell, something like this. And there are glide planes. So again, we have glide planes going through the object. So say if we look at this squiggly rainbow, if you mirrored it, the squiggliness would kind of go in the opposite direction, like this. And then if you translated half a unit cell down, you would end up on this squiggly line. So these are all related by this glide plane. We also have glide planes in between these squiggly rainbows. So say if you were to start off with this point here, if you were to mirror it opposite this glide plane, you would end up with the squiggly, but in the opposite direction. And then if you translate it half a unit cell up, then you end up on this position here. So these two are related by this glide plane. So like I said, glide planes, it might not be so easy to spot them. So in 2 dimensions, we talked about this. We have 5 different crystal systems. We have the oblique, rectangle, centered rectangle, square, and hexagonal systems in 2 dimensions. And we can have different plane groups. So I just want to, this is just one example of a plane group. The name of the plane group is P4MM. That's, describes the combination of symmetry in that particular plane group. So the P, it indicates if it's primitive or centered. In this case, it is primitive. The 4 indicates that we have 4-fold rotation. This M tells, so usually you have, the primitive or centering is usually what's described first. Then typically you have, rotation that's described, and then mirrors come later on, or glides. So in this case, we have two M's. This indicates that we have two different mirror planes that are not related to one another. So these are examples of other plane groups. P6, it's primitive. There's a six-fold rotation. There's no mirror in this case. That's just the end of the name. P6, that's it. CM is another name of a plane group. It's a centered lattice with mirror symmetry, but there's no rotational symmetry there. So then there is no integer number in this plane group name. So plane groups, they can have different names. So these are all 17 plane groups. P1 is the one with lowest symmetry. It just has translational symmetry, but no other, there's no rotation apart from, one fold, but there is no other form of rotational symmetry. There's no mirror plane, there's no glide plane. Let's look at the P2MM. Let's look at this one here. So there's it's primitive. It has two-fold rotational symmetry. You can rotate it 180 degrees. Now there's two mirror planes, two unique mirror planes. There are mirror planes that are vertical. So there's I can see that there's a mirror plane going through the middle of these rectangles, but also say a mirror plane that would go along the edge of the rectangle. And there's also horizontal mirror planes as well. Now, yeah, so the horizontal and vertical mirror planes are not related to one another by mirrors, by symmetry. So these are two separate mirror planes. Now, if you look at P4MM though, so again, it's primitive. Here we have fourfold rotational symmetry, so we can rotate it by 90 degrees. And we have two M, so we have two unique mirror planes. Now, in this case, the vertical mirror plane and the horizontal mirror planes are the same in some sense. They're related by symmetry. So if you take a vertical mirror plane, and if you were to rotate it 90 degrees, which we can do because we have fourfold rotational symmetry, then that vertical mirror plane becomes the horizontal mirror plane. They're related to one another by that fourfold rotation. So actually the second M is not the vertical or the horizontal mirror plane. It's yet another mirror plane. In this case, we have a mirror plane going along the diagonal as well. So the two diagonals have mirror planes as well. So that's why we have two M's here. We have two mirror planes which are not related by any form of symmetry, two unique mirror planes. And then also another one that I want to point out, P31M and P3M1. They have the same symbols, but the positions of the symbols are different. So what's the difference between these two? Well, we can have a closer look. So this is again the 17 plane groups, but shown in a different way. Here we have those symbols that I've been showing before. So a square represents a fourfold rotation axis. Here, though, instead of these ovals, we have these diamonds to represent twofold rotation. Yeah, and then solid lines correspond to mirror planes, dashed lines correspond to glide planes. So the difference between P3M1 and P31M, since the names are quite similar. So they both are primitive lattices, they both have threefold rotational symmetry, and they both have mirror planes. But the difference is you can see that the relative positions of the mirror planes are different. So for example, in P31M, there's a mirror plane that goes along this kind of short diagonal here, and also along the edges of the unit cell. Now in P3M1, you don't have mirror planes kind of going around the edge of the unit cell. And you don't have that mirror plane along that short diagonal anymore. Now you have a mirror plane going along the long diagonal, and also in all of these other directions. So the difference between these two plane groups is just the relative positions of the symmetry elements. So be careful. And also I want to point out that the name of the plane group doesn't actually tell you about all of the symmetry elements in that plane group. So for example, in P6, you have 6-fold rotational symmetry, as the name suggests, but you also have 2-fold rotational symmetry, these diamonds, and you also have 3-fold rotational symmetry, these triangles. So the name itself doesn't tell you all of the symmetry elements that are in there. You actually kind of need to look at these diagrams with the symmetry elements to actually be able to tell all of the symmetry operations that are actually coexisting in this plane group. And with, yeah, as you see, with P6mm, there's a lot of symmetry in there. It gets quite messy, these diagrams. So I think we have 13 minutes left, according to my watch. So let's do some examples. So I've done some examples, but I want you to think about these other examples now. Again, sorry, there's a typo here. It's multiple choice, but there should be 2B as an option, but that doesn't really matter. What matters is the plane group, which is the answer. So I have a picture of a fence. I want you to ignore the background completely and just imagine just the fence itself, the wooden bars. But imagine this as a 2-dimensional object. But keep in mind, there is like this plank in front that kind of blocks the one in the back. Yeah, I want you to think about what plane group is shown in this picture if you ignore the background. So I'll give you a minute to maybe think about this. And if anyone has an answer, please speak up or mention it in the chat. And maybe I can give a hint. I always like to start off thinking about what is the unit cell. So I'll start off by providing this hint. So this is a unit cell that I've picked, and try to think about what symmetry elements that you can see within one unit cell, just to simplify things a little bit more. Any guesses yet?
I could guess.
Yes, if you have one.
Should I explain it or just say it?
Saying it is great, but explaining it would be even better.
So maybe P2mm?
Yeah, that's correct. And I have some, maybe I can help with the explaining because I can draw on this page. So, but that's absolutely correct. So it's P2mm. So in orange, I've drawn all of the 2-fold rotation axes, and the green lines are all of the mirror planes. Now, again, in this case, these mirror planes are not equivalent to these mirror planes, because if you rotate this mirror plane 180 degrees, it ends up looking the same. It doesn't end up becoming the opposite diagonal. So these 2 mirror planes, these 2 sets of mirror planes are different, which is why we have 2 M's in the name, P2mm. Great. And this one is a really tough example. Since we're a bit short on time, I'll explain it. So this one has a glide plane. So this is a unit cell that I picked. And these are the glide planes. So say we start off with this brick. If you first mirror it, you end up with this brick, but then if you translate it half a unit cell, you end up there. And then you can repeat this again to get that brick. And there's also other glide planes which give you these other bricks as well. And there's also glide planes that go in other directions too. So say we start off with the first brick again. If you mirror it across this glide plane, you end up with this brick here. And if you translate it now down the unit cell, you end up with that right there. So again, we have glide planes in both directions. So it's PGG. All right, so I know we only have 9 minutes left. So I'm not sure if we have sufficient time with this. We have a few minutes, so try to get through a few of these examples if you can. So actually, so in the shared box folder, I put in some slides that contain, plain wallpaper actually. So the exercise is to find a unit cell and try to find the symmetry elements. So I think this works a lot better in the classroom because people can work together in groups and discuss things. And I think it's a good exercise because it helps you see symmetry better. And that's something that's really useful if you're a crystallographer, to be able to identify the symmetry yourself by eye. Because sometimes you end up with, working in the wrong space group, and it's important to be able to catch that. So for example, maybe, since we only have very little time, I guess there's not so much time to actually go into the box and look into this yourself. But maybe I'll leave this page open. Yeah, like I said, there's 17 examples. So of these, there's one example of each of the 17 plane groups. So I think if you have time later on, this is a really good practice, and I hope a little bit more fun. But let's say, yeah, I'll keep this page open, and then maybe you can think about this. What sort of symmetry do we have here, and maybe what sort of plane group that we have. And in this case, be careful. The colors represent different objects. So this light tan and dark tan square are not the same. They're different. I think maybe I'll probably stop recording here because I think there's going to be a long silence. So, and this is pretty much, we've reached the end of the lecture essentially. So I'll stop the recording now. So I'm going to stop sharing for a second to stop